A 2 kilogram bucket is attached to a massless string that is wrapped around a 1 kilogram, 4 centimeter diameter cylinder, as shown in the figure. The cylinder rotates on an axle through the center. The bucket is released from rest 1 meter above the floor. How long does it take to reach the floor? Okay, so we already have a picture, which we just took from the example, and we have free body diagrams. Remember, this is a torque problem, so we'll be using something about torque in order to go along with our calculations. We have this bucket, and that the bucket has its own free body diagram, like right here. This is the bucket, and this is my cylinder here. So if I want to look at the bucket, I'm going to do the Newton's second law. Sum of the forces is equal to ma. And I'm going to follow the direction of A. So here we can see that A is pointing down. Mg would be down. So here we can see if A is down, Mg is down, and T is up. So I'm going to have Mg is down minus T, because T is up, is equal to Ma. And now I need to somehow link the acceleration and the tension. And so this is where I'm going to use torque. So one of the things I know is that there's a torque of my rotating cylinder, and so I know that that my torque is equal to I alpha, and I want to find alpha. So I'm interested in alpha. So alpha is equal to the torque over I. And why do I care about alpha? Well, I know there's a relationship between alpha and A. And so we'll get to that in just a minute. So we know that alpha is equal, A is equal to alpha times R. And so my acceleration is related, my linear acceleration, this A here, is related to my angular acceleration, alpha. And so I'm just going to use this equation to relate them. But first I'm going to find alpha. So alpha is equal to the torque. And the torque is, remember, torque, right up here, torque is also equal to R cross F. Okay, and so if I think about my cylinder, this rope is pulling due to the tension of the bucket. And so my R here is going to be capital R, and the only force acting on my cylinder is the tension, so I'm going to have tension. And now the angle between them, if I think about where the rope is and the radius, they're perpendicular to each other. So the rope pulls on this cylinder down, right? And my radius is directly perpendicular to it. So I'm just going to have RT for torque. So I'm going to plug that in down here. So I'm going to have R times T over I. And so what is I for? I for the cylinder is equal to 1/2 capital M R squared. And M, capital M, right, is the mass of the cylinder. Little m is the mass of the bucket. So here I'm going to have 1/2 M R squared. And so now I can plug this into A, right? Since I know my A is equal to alpha R. So my A is equal to R times T over 1/2 capital M R squared, and then times that R. So I have, I can see I have an R and an R on the top, and I can cancel them with my R squared on the bottom. So then A becomes, well, actually, we want to solve for T in this case because we'd like to be able to keep our A, because we need that in order to use an acceleration and use the kinematic equations to find delta y and then time. So we're going to write T in terms of A. And so we can, whoops. Okay, so here we have then T is equal to 1/2 and we'll put the M on top times A. And so we're going to plug that in to our equation over here. So we're going to have mg minus t is equal to ma. And so we have mg minus m, capital M over 2 times a is equal to ma. So now I can add capital M over 2 to both sides. These cancel out and I get mg is equal to, I'll get an a from both of these, a times little m plus big M over 2. So now I'm looking for, I'm trying to solve for a. So a is equal to mg over, I'm just dividing both sides by this piece right here, little m plus big M over 2. And when I plug in my numbers, I'm going to have a is equal to 7.84 meters per second squared. And now I need to use a kinematic equation. So I'm going to use y final is equal to y initial plus VIY delta t plus 1/2 a delta t squared. Okay, so let's go back and look at our picture so we can figure out our y's. And we'll notice too that our a is pointing this way. So my y final is going to be 0. But my y initial here, if I'm moving this way, right, if I'm moving down, then instead of y equals 1, I'm going to say y is equal to a -1 because the positive, I'm saying positive y is down. So this is positive y is down. So usually something behind me is going to be, especially heading towards 0, is going to be negative. And then I get to 0 and then I start increasing in my y value. So I'm letting my y initial equal a -1. So I know my y final is equal to 0. I know I don't have an initial velocity, that's equal to 0. So I get my negative y initial is equal to 1/2 a delta t squared. So I'm going to multiply both sides by 2 over a, 2 over a, and that gets rid of these terms here. And so my delta t is equal to 2 times y I over a, and that's going to have a negative in it, square root. And now remember my yi is a -1, so my delta t is equal to a -2 times a -1 meter divided by a is 7.84 meters per second squared, and I got to add in my square root. So therefore the delta t, the time it takes for that bucket to hit the ground, is 0.5 seconds.